Last episode, the agent wrote and ran code inside a sandboxed exec node, and every byte of that run was real. But each run started from nothing. Today, we give the agent a memory that survives a stop, run a graph to a checkpoint, kill it, and resume on the same thread. The state reloads exactly because persistence is just a dict you can save and load. Here's the lie we're killing. Memory sounds like a black box that remembers things. It isn't. It's a state dictionary, a list of messages, a token count, and a checkpointer that writes a copy of that dict after every node, keyed by a thread ID. Watch one turn. The model node appends a message. The count node adds its tokens to a running total. After the node returns, the checkpointer takes a snapshot. The whole state frozen, stamped with the thread ID. That snapshot is the memory. Now we stop. The process ends after turn 2. The graph object is gone, the variables are gone. But the checkpointer still holds 3 snapshots under one thread ID. Nothing was lost because nothing lived in the process. It lived in the saver. Resume. We rebuild the graph, hand it the same checkpointer and the same thread id, and call it again. LangGraph reads the latest snapshot, restores the state, and continues from turn 3. The history is intact, the token total keeps climbing from where it stopped. And because the state is plain data and the model is scripted, both halves of the run are deterministic. The size after each turn is a fixed number. Reload it tomorrow, reload it twice in a row, same curve, same digits. The program. We import our harness, build a tiny state graph whose state holds a message list and a token total, wire a model node and a counter node, and compile it with an in-memory saver. The scripted model gives 5 fixed turns. The state schema messages a list and total tokens and int. The model node pops the next scripted turn and appends it. The count node adds that turn's token cost, the length of the message, to the running total. Pure functions over the decade. We run turns 1 and 2 on thread T7, invoking the compiled graph twice with the saver attached. After each turn, we read the snapshot, the checkpointer wrote, and record the cumulative state size into our trace. Now we simulate a crash. We throw the graph and app away entirely. Then we build a brand new graph object, hand it the same in-memory saver and thread ID, and invoke turns 3, 4, and 5. It picks up the message history and the token total from the saved snapshot. Run it. The terminal prints memory after every turn, 5 rows climbing, and marks the row where we resumed. Then it runs the whole thing twice in process and asserts the 2 traces are byte identical. The hero figure is a memory growth line, cumulative tokens per turn, with a vertical marker at the resume point. The line doesn't dip at the resume. It keeps climbing, proving the reload restored everything. That's the insight. Persistence is state in a dict you can reload, which is exactly why offline memory reproduces to the digit. Next episode, we stop only reading old snapshots and start editing them. Interrupt and time travel, pause the graph, branch from any past checkpoint, and let a human steer.